Hi everybody, and welcome to a new video in the video series on systems biology, digital twins and AI. So, we are now still in block 2, so we are still using data. We have done the optimization and we have done the uncertainty analysis of the parameters, or if we want to, we do that. And now we are looking at the uncertainty of predictions. So a core question here is if they are well determined. If they're well determined, you can call them core predictions. So the question is, are the predictions core predictions? Are the prediction, which we here call y-hat pred, are they uniquely identified given the model and this concrete data set? So again, here we are looking at the practical identifiability analysis for the predictions. And if it's not for the parameters, you don't call it identifiability analysis. Typically, you call it either core prediction analysis or more commonly observability analysis. Okay, so what will we talk about? We will talk about this sort of importance of looking at the uncertainty of predictions, and if you just have a simulation, you don't know if it's a core prediction or if it's just what we sometimes call a beach statement, which is not a very strong statement. And then we look at just to understand some of the problems with just using the profile likelihood as it is. And then we look at some alternatives. So we will look at one called bootstrapping, one called MCMC, and then we will return to this profile likelihood analysis and we will see a modified version, a sort of core prediction type of analysis version of that for predictions. So how can you modify the original profile likelihood to the situation of predictions? Okay, so that's the video. So here we have a simulation with respect to time and we have some kind of prediction. So each line here corresponds to a simulation for a parameter that shows a good agreement with the data. So we can't really say which of these parameters that is the right one. Therefore we have to consider all of them. And here we see that there is a big difference between different types of predictions. So here the prediction at the end is that they all end up here. This is a very well-determined prediction, and this would then be what we call a core prediction. But here, an individual line here, that the value of this particular thing that we are predicting here is this. That is just a suggestion. It could be like that. It could be like this. It could be much lower. And the model and the data that we have gives us no information at all that it should be like that. It's just a suggestion. It could be like this. It could be in some other way. And here it's important. If you ever see a model and you just see a line, that's just a suggestion. That's just a suggestion. If you don't see the uncertainty, don't believe that it's anything more than a suggestion. And that basically means that the only thing you're saying is that it could be like this, could be in some other way, and the model doesn't really tell us which is the right one. There is nothing in the data and the model that we have that gives us any information that it should be like this or in some other way. That's basically what you could say already before. So why bother doing the model? There are some subtle reasons why it still has some information to be able to say that, but it is a very weak statement. You could almost lie on the beach and not even do the model and just say, well, it could be like this, could be in some other way. I don't know. So let's lie here on the beach instead and just chill out. So you should be very wary when you see a simulation and you don't see an uncertainty like this. Then remember that they are all just suggestions. They are all just beach statements. Okay, so now we understand the importance of having the uncertainty of a prediction. So let's understand why we can't just apply the identifiability analysis that we already did. So again, identifiability analysis asks, can a parameter pi be determined? Observability analysis asks, can a model property, theta or ypred, or whatever you want to call it, be determined? And here it's important to realize that identifiability, if all parameters are identifiable, if all parameters are uniquely determined, then the predictions will also be uniquely determined. So if you have identifiability for all parameters, then you're happy. But you don't have to have that. So in this example that we had with these two ways of eliminating A, we know that we have problems that identifying them uniquely, but the sum of them, that we can determine. So the total amount of elimination, and that also means that the dynamics of A we can identify. So all predictions that just have to do with the dynamics of A, those are very well determined. So that means that we can have observability, we can have a core prediction, even though there are parameters that are completely non-identifiable. So all of this means that identifiability analysis has some usefulness, especially if you want to know the values of the parameters. But it's not sufficient to know whether a prediction is a core prediction. So for that, you need to do observability analysis. And the problem with doing this profile likelihood approach is that now you can no longer set a parameter to a value and you just do the optimization. So that's why it's a slightly more complicated in this situation. And we'll come back to how to modify the profile likelihood analysis. But first, let's look at two other alternatives. The first of them is called bootstrapping. This is something that you can use always. It's very robust and it's decent. I think it's better than some of the alternatives that I warned against, like the Fisher information matrix and structural approaches. So if you can't use some of the really best approaches, which the profile likelihood, the prediction profile likelihood approach, or if you can't use Monte Carlo MCMC approaches, then you can always fall back on the bootstrap. So it basically says, if you have some original data series and you have some property that you want to determine, then you can create a number of bootstraps, which are basically modified versions of the time series of the original data series. So you have some kind of property here, ypred or theta or whatever you want to call it, which depends on which you can determine using this optimization from the original data series. And you can also do it for each of these these bootstraps that you created, each of these sort of alternative data series. You can also use you can also do the same optimization. And then you simply look at what is the distribution, how different are these values, these predictions? Are they the same? Then it's a well-determined prediction. If they are very different, then it's not. So this is the simple idea. It's very simple. You just create these bootstraps. And there are different ways to do that. Either you can do a non-parametric approach, sampling with replacement, or you add a null hypothesis, so you use a model basically. So let's look at the first alternative to create these bootstraps. So you have this original data series, y1, y2, all the way up to yn. And then if it's a non-parametric, you do sampling. So you want to create a bootstrap, the first bootstrap data series here. Then you draw a value. and you put it back again. So drawing with replacement, and then you do that until you have a bootstrap, which is some version of the time series. And here you see that because you have this replacement, you can actually get the same value twice. And then you do that many times, and you generate as many bootstraps as you want. And again, you apply the optimization to each of these. You get different values, and depending on how similar they are, you sort of have a feeling for the uncertainty of the property that you want to predict. So that's the non-parametric approach, drawing with replacement. The other approach is to actually use the model. So you train the model to fit the parameters, and then use the model to simulate, and you add noise, and you add a new realization of the noise each time. And in this way, you generate new time series. So here again, you can generate as many bootstraps as you want, and this allows you to again do the optimization, determine the property that you're interested in many times, and you have a distribution, you have the uncertainty. Okay, so that's bootstrapping. Now let's look at the other approach, which is maybe even more theoretically sound, which is called Markov chain Monte Carlo approaches. It's very strong, it's very general, but it does have some crucial limitations, and I will get to those in the end. So Markov chain, the first part of the name, is that you do something again and again while forgetting everything except for what you see right now. So basically you have a state that you update, and the state tells you everything about the history. So that's a differential equation is a sort of special case of that. And then you have the Monte Carlo part, which is that you draw something random and you determine something at random based on that. So we've seen several examples of that in the optimization algorithms and so on. So the combination of those two is called MCMC, Markov chain Monte Carlo approaches. And you can use this type of approach to approximate the likelihood function. And one common special case of MCMC is to use something called the Metropolis-Hastings algorithm. And this can be applied as long as you have access to a function, like the cost function here, which is proportional to the true function. So you want to have the likelihood function, or you want to have the shape of the cost function, and you can calculate it. And it doesn't even have to be the actual function. It just have to be something that's similar enough to it, so to say. And then basically what you do in this Metropolis-Hastings approach is that you have some initial distribution. So you have a prior. So you need to have this prior belief. And basically what you're doing is that you're updating this prior. So this is similar to the idea of this ref set, for instance, that you're all the time updating in the scatter search. So you have some sort of prior belief, and then you update it. And you update it by adding points to it. So you are at a specific point in this parameter landscape, and then you draw a new point, and you draw this new point based on the current belief. So you are more likely to draw it here in the middle where you already have lots of points, but you can draw it basically anywhere because there is some probability that you will draw something basically everywhere. And then you will add this new point if the new point has a lower cost, you will add it. So you update this distribution based on this point. And if it has a higher cost, you might also add it, but you only add it with the probability. And the probability, as usual, depends on how much bigger it is. So basically, this is it. In this way, you sort of add points, and you are more likely to add points where the cost is good, so the cost is low. And therefore, you will have more points here. So basically, the density of points, that will be your posterior distribution. Okay, so you go from a prior distribution to a posterior distribution by adding points in this way and seeing how the cloud of points is updated. So that's basically how you do in MCMC approaches. And this point cloud then is sort of an approximation of the uncertainty of either the parameters, or if you do simulations of a property for all of these points, you get the uncertainty of that property. So let's now finally return to this approach that we used for the identifiability analysis when we looked at parameters, and see how we can modify that so that some version of that can be applied also to prediction uncertainty. So in the first step, you either do an optimization or you do a Monte Carlo analysis to get the point cloud. So you get acceptable parameters that are below some certain cutoff. And then you looked for shared properties. So that gives you a feeling for what is the uncertainty of something. And then in step 2, you pick a prediction that you're interested in. And then you look specifically for the uncertainty of that prediction. In the same way as in the profile likelihood, you pick a parameter and you look at the uncertainty for that prediction specifically. And here you can't set the value because it's not a parameter that's constant, it's a model property. So what you're doing is that you are doing a constrained optimization problem, where the constraint is that is one of two things. Either you turn everything upside down and you say that I'm not going to optimize the agreement with the data. I'm going to optimize how big this particular prediction can become, while fulfilling the constraint that it should be acceptable agreement with the data. So you're not optimizing the agreement with the data, you're optimizing the prediction, how big it can become, while still agreeing with the data. So you are maximizing some prediction here with the additional constraint that it should be below some cutoff. So that's one way to do it. Another way to do it is to and this is more similar to the traditional profile likelihood. We are following the profiles. So you are adding the constraint that you have some prediction. So here I'm calling it theta and here I'm calling it ypred. It's the same thing. So you're stepping in this prediction. And then you are adding the following term to the cost function, where W here is a very big number, and you have the predicted value, which depends on the parameters, and then you have the value that you want to have, so theta prime or ypred prime, and then you use this cost function. And if W here is a very big value, the optimization will ensure that ypred that depends on the parameters is equal to this particular value that you have set it to, so that you are stepping. And this is how you do the same type of stepping as we did for the parameter. It's just that you're doing the stepping now in a prediction, which you cannot set, but you can make the optimization fulfill this constraint. So this is a sort of way to do a constrained optimization, that you sort of add this punishment to the cost. So that if it doesn't fulfill this value, then you get a very high cost. So therefore, the optimization will always ensure that it's fulfilled. So that means that you can get these type of curves again. So here we have a prediction profile likelihood curve. This is the optimal value for a particular prediction. And here we have the agreement with the data. So then as you are stepping away from this, you get a worse and worse agreement with the data. So for each step here, you are stepping away and then you're optimizing. So this is the best possible agreement with the data that you can have for these other values of this prediction, which here is called EC50. So here you want to determine the value of EC50, which is not a parameter, it's a model property. And then you're adding this constraint, you're adding this punishment term to the cost function to make sure that the optimization will find the best possible cost where it's fulfilled that is EC50 is equal to this value. And then you see that you have this trade-off and you have this very nice U-shaped curve here. And this U-shaped curve is simply an indication that this particular model property is quite well determined. And in this particular case, we see that we can actually determine EC50 in a way that is almost completely non-overlapping with how you usually determine. And this is the more correct approach. So these show that sometimes you might need a model to determine something as basic as EC50, where you have the half maximal activation. Okay, so that's a paper from 2015. So here are some of the papers where I'm presenting this stuff, and there are parallel developments done by other research groups as well. I did some reviews where I compared different developments. So I just in the very end here want to say that once you have done all of this analysis, you can also do a validation test, which is like the third step, so to say, in this core prediction approach. And that is by saying, okay, so we have this upper and lower boundary for the prediction. So this is the upper value, this is the lower boundary. So we have this boundary. Now we want to check that that's actually true. So that's one way to do that is to add the new data point, which is outside this core prediction interval. And then you see, would that lead to rejection of the model? So then you are simply optimizing the cost for this expanded data set, and you see, can you get an acceptable agreement with the data? So that's this cost function for this expanded data set where you added this data point that lies outside of the core prediction interval. Does that pass a statistical test? If it does not, then that's a sort of confirmation that your intervals are good and that you didn't follow a local branch, you didn't get stuck in some local optima, you didn't fail with the optimization, and so on. So this is a validation step that you can add in the end if you want. So that was it. Now you know how to calculate uncertainties, not only of parameters, but also of predictions. So that was it for this recording. In the next video, we will look at the statistical tests that I mentioned here.